Hi everyone, my name is Emma Hayden and this is my Lab 3 report on black hole and orbits. The goal of this lab was to create two computational models that apply the universal law of gravitation and Newton's second law, also called the momentum principles, to simulate orbital motion. I used GlowScript for both parts of the lab to visualize and analyze the motion of celestial objects. In part 1, I modeled the motion of a star orbiting a black hole to estimate the mass of the black hole based on gravitational interactions. In part 2, I simulated a spacecraft's orbit around a planet and its moon, testing whether I could achieve a stable figure 8-like orbit. These simulations help show how gravitational forces in motion are connected through computational modeling. This is a preview. This lab was based on Newton's law of universal gravitation, which says the force between two objects is proportional to the product of their masses and inversely proportional to the square of their distance, and Newton's second law, which relates the net force to the rate of change of momentum. These principles form the foundation for both of my programs. In addition to that, we have the velocity update formula, the position update formula, the gravitational formula, and then Fnet is equal to Fnet parallel plus Fnet perpendicular. For part 1, I modified the starter code to include my own email as a seed, which generated unique star position data. I calculated the velocity and the momentum changes in both the parallel and perpendicular directions and used the gravitational formula to estimate the black hole's mass. For part 2, I used the second starter code to calculate all the gravitational forces. The force on the moon due to both the planet and the spaceship, and the force on the spaceship due to both the moon and the planet. I then used the position and velocity update formulas from Newton's second law to make the simulation run. In part 1, my system was the star and its surroundings were the black hole, and in part 2, my system was the spaceship and the surroundings were the planet and the moon. This identification helped me know which forces to include in my net force calculations. Here's a preview of my part 1 code. I added sections to calculate net force components, momentum updates, and used the given position data to computate acceleration. The code allowed me to estimate the black hole's mass from the star's motion. The estimated mass of the black hole, MBH, came out to be approximately 1.19 times 10 to the 34 kilograms. As the star got closer to the black hole, the force arrows grew larger, showing the increase in gravitational pull. The results followed Newton's law of gravitation closely, although small differences appeared due to rounding and the discrete nature of the simulation. For part 2, I defined all constants such as the gravitational constant, planet mass, moon mass, spaceship mass, and time step. I determined that the best initial velocity values for my spaceship were 25 meters per second in both the x and y directions. This gave me an orbit that interacted with both the moon and the planet without crashing. And here's some more of the edited code for part 2. I included calculations for the net force on the moon and the spaceship, and used Newton's second law to update both their velocities and position over time. The simulation successfully showed gravitational interaction among all three bodies. Some possible sources of error included small calculation mistakes, rounding, and trial and error adjustments of the spaceship's initial velocity. Because the code used manual tuning for stable orbits, it was easy to overshoot or undershoot certain velocity values. Using the same initial velocities, 25,000 in both the x and y, the motion clearly showed how the planet and moon's gravitational pulls affected the spaceship. While the orbit wasn't a perfect figure 8, it still demonstrated how Newton's laws govern the motion. The results matched theoretical expectations that both forces influence the trajectory simultaneously. In part 1, the net force on the star is equal to the rate of change of its momentum, meaning they both point in the same direction. The parallel component of the net force changes the star's speed, speeding it up or slowing it down, while the perpendicular component changes the direction of motion, curving the orbit. This explains why momentum changes continuously, even though the star's speed might stay nearly constant in parts of the orbit. If we extended the model to include the black hole, star, planet, and moon altogether, we would need to calculate gravitational forces between every single pair of objects. The dominant interaction would definitely be between the black hole and the star because the black hole's mass is so huge. The planet and moon would form their own smaller orbital system, but even they would feel weaker gravitational effects from the black hole and star. So to predict the entire system's motion accurately, we'd have to include all these interactions in our computational model. Overall, this lab helped me understand how computational modeling connects the equations of physics to real-world motion. By adjusting code and observing orbits, I could directly see how Newton's laws explain gravitational behavior across vastly different scales, from stars to spaceships. Thank you for watching.